Let us look at the line length balance method. AB is a folded layer and we want to balance it. Before deformation, usually the layers are straight. So, how much is the straight length of AB? In other words, we want to find out this length and then we will straighten it. We break this AB length into several short segments. The first segment that I have drawn is 1 centimeter, the next segment is 1.6 centimeter, the next segment is 1.7 centimeter, the next segment is 2.8 centimeter. Therefore, the curve AB length is equal to 7.1 centimeter. Before deformation, the AB curve line is expected to have a length of 7.1 centimeter. This is after restoration. Unfortunately, not all folds have such simple geometry. It is possible that a folded layer extrados has one geometry and the intrados has another geometry. I mean to say, the AB lines geometry and the CD curve lines geometries are not the same. So, if I do line length balance method for AB line, there is no guarantee that it will be same as a CD curve line's length, not always. In that case, the line length balance method will be problematic. What is our expectation? Our expectation is that this long rectangle with AB and CD of same lengths. Since the curve lengths need not be the same, we may not be able to come back to this position. This creates a problem and one can think what else can be done. Maybe we go for the area balance method. Consider boudins 1, 2, 3 and 4 and they are the rectangular boudins. I have intentionally not drawn the perfect rectangular shape because that is a natural situation. Suppose we want to restore it, what to do? I will measure each of these lengths. L1 is equal to 1.7 centimeter, L2 is equal to 0.5 centimeter, L3 is equal to 1.8 centimeter and L4 is equal to 1 centimeter almost. Therefore, the sum of these lengths is 5 centimeter. Let us find out this length by measuring. B is equal to 0.5 centimeter. So, after restoration, it will be a rectangle of 5 centimeter length and 0.5 centimeter width. Here the length is 5 centimeter and the width is 0.5 centimeter. In this process, both line length and area have been balanced. Why? Because in these cases the areas are A1 is equal to 1.7 centimeter multiplied by 0.5 centimeter. For the block 2 it is 0.5 centimeter multiplied by 0.5 centimeter. For block 3 it is 1.8 centimeter multiplied by 0.5 centimeter and for block 4 it is 1 centimeter multiplied by 0.5 centimeter. If I add up the areas, I find it is same as Li multiplied by B. This is Li which is 5 centimeter and this is equal to B. So, both line length and the area have been balanced. From here, a compulsory exercise for students, although very simple, you must find out the elongation E, which is the length final minus length initial divided by length initial. Where is the length final? It is from this pin line to that pin line distance. How much is that? It is 6.8 centimeter. So, 6.8 centimeter minus 5 centimeter divided by 5 centimeter. Did you note that the change in length delta L, which is LF minus Li, can also be found out if I sum up these distances. the inter-boudin distance, which is the sum of the inter-boudin distances. Students have to find out E, then stretch, then quadratic elongation, reciprocal quadratic elongation and fundamental strain. You have to keep on doing this repeatedly, also the percentage elongation to be found out. These are the pin lines final, and I can draw the pin lines here calling pin line initial. I can consider that this pin line is static and this pin line is movable. In other words, we are calling it as a loose line and this one is a loose line, which means as if this block was static, only extension has happened in this way and different parts have been broken. Take the lift off structure, and in one case we are going to apply line length balance and in another case we are going to apply the area balance. This one is the pin line and this one is the movable pin, or we take as the loose line. To apply the line length balance, I need to find out the AB length, add with the BC length, add with the CD length, add with the DE length, add with the EF length, add with the FG length. AB length in my diagram is 1.2 centimeter. The total is 7.1 centimeter. Now the loose line is to move, and from A point and on the AG line I will draw 7.1 centimeter. The A dash length is equal to 7.1 centimeter. Next, I will drop a normal from A on the detachment and say that by line length balance method this restoration has been made. Next, I am going to do the same exercise. I am not saying whether this is right or wrong, just moving into the area balance method. In this case, we have to find out the area bound within this region. This region can be broken into a rectangular area and a triangular area. For the rectangle ABCD, the area is 1.5 multiplied by 1.9 centimeter square, which is 2.85 centimeter square. The area of the triangle ACD is given by half AD length multiplied by the normal length, which is here 0.5 centimeter. AD length is 2 centimeter and CM length is almost 0.5 centimeter. So the answer is 0.5 centimeter square. So the total area is given by 2.85 plus 0.5 centimeter square, which is 3.35 centimeter square. Now we want to find out this length, which is 2.5 centimeter. Divide this length by 2.5. 3.35 divided by 2.5 equals to 1.34 centimeter. Now I have to draw a line of 1.34 centimeter in this direction from this particular point. This length is equal to 1.34 centimeter. From this point I will drop a normal on the detachment. We say that this deformed layer before deformation was of this geometry. In this process, area balance has been made. Which two areas have been made the same? This area is equal to that area. This loose line is now thought to be present here. This is the loose line initial and this is the loose line final. how much is the rectangle's area? 2.5 centimeter multiplied by 1.34 centimeter and is equal to 3.35 centimeter square, which is the area A0. So, we have two possible solution by line length balance and area balance. When line length balance has been made, area balance is not done. Clearly, this area is less and this area is much more. Whereas, when area balance has been made, most likely line length balance has not been done. Let us start with a box fold. Here is a box fold and we want to do an area balance. Consider that the box fold has generated over a detachment. This is the detachment below which there is no deformation and above which there is deformation or folding. Now, we want to find out how much is the area bound by ABCD rectangle. It can be square, it can be rectangle. The area is given by AB length multiplied by BC length, which is equal to 1.9 centimeter multiplied by 2.7 centimeter, which is equal to 5.13 centimeter square. This area has been produced due to a compression. Consider here the loose line in the final position. We have to locate the loose line in the initial position. We find out this distance. The depth of detachment in this case is 2.1 centimeter. D equal to 2.1 centimeter. Divide 5.13 by 2.1 and we get a dimension S, which is equal to 2.4 centimeter. We have to draw this S length on this line and in this direction. This length is equal to S. S is 2.4 centimeter. Now, from this point I will drop a normal on the detachment. I am extending a bit the detachment and I am calling this as the loose line initial. Now, you can note this area A0 is equal to this area A1. What we have done is D multiplied by S. D multiplied by S is taken as the area A0. A0 was calculated, D was straightway taken from the sketch and from there small s was obtained. Then small s was drawn, a normal was dropped on the detachment. Now, we can comment that the box folded layer, which was of this size and shape, has come from initially a rectangular layer. Do you note that we do not do anything with this area? The reason is, suppose this area is A2, the initial area before deformation is A2 plus A1 and after deformation the area has become A0 plus A2. A2 can be cancelled and we did A1 is equal to A0, therefore, our deduction holds true. Suppose instead of doing area balance, one goes for line length balance, then also one can restore and the question remains which one will be preferred, area balance or the line length balance. Consider a simple case of a reverse fault having a flat ramp and a flat geometry and the soft hanging wall material has moved over this fault with a divergence in this geographic direction, which is same as the foreland direction. This is the hinterland direction. From this figure we have to balance the cross section. Let us apply the area balance method. Let us draw a faint line joining these 2 points and in my diagram this line is parallel to that line, the flat. Also in my simplistic diagram this line is parallel to that line. Now we can see a trapezoid formed A, B, C and D, and we want to find out the area of this trapezoid. Let us apply the formula. It is equal to half AD plus BC multiplied by small h. Small h is, in this diagram, this vertical distance which is equal to 1.4 centimeter. The AD length is 3.6 centimeter. The BC length is 6.8 centimeter. Therefore, the area of the trapezoid is next. Find out the distance xy, this line length. Xy length is 1.3 centimeter. I divide 7.3 by 1.3 to find out the length, 5.6 centimeter. Consider this line as the loose line final, and I want to locate loose line initial. To do that, I have to move 5.6 centimeter along CX line and in this direction. So, let us first of all extend the CX line. Next, let us measure 5.6 centimeter. This distance is equal to S is equal to 5.6 centimeter. Next, I extend the detachment for the sake of completion of my drawing. I extend this flat and then I drop a normal from this point on this surface. Now, we can say that the faulted hanging wall block, which was of this shape and size, was actually of this geometry before the deformation started. So that what has happened, the area loss here due to compression given by S multiplied by the xy length, here is S and here is the xy length, has been equal to the area gain over here given by the area of the trapezoid what was obtained. So, the loose line initial is here. We have considered this point B was initially at this place before deformation, and this point X before deformation was here as X dash, which means the line B dash X dash before deformation has transformed to line Bx after deformation. In this sketch, B dash X dash length is 11.7 centimeter and the Bx length is 7.8 centimeter, which means along this axis, the T axis, along T axis, there has been a shortening that was expected because reverse faulting is produced due to shortening in the shallow crustal domain. The length final is the Bx length and the length initial is B dash X dash length. Now, students have to find out the shortening percent, quadratic shortening, reciprocal quadratic shortening and fundamental strain. Students must do this and do not ignore this simple exercise so that you become fast in calculating these parameters.